In this module, we're going to cover slightly more advanced material dealing with models for qualitative dependent variables, specifically the spatial Probit and the spatial Tobit models. And we'll have three sets of slides. In the first set, I will review some basics about the Probit and the Tobit model. If you're familiar with these models, then you can skip this section. The second section then deals with the specification of the spatial Probit and spatial Tobit models, the lag and the error version. And then the third section deals with the specification tests and estimation of these models. So first we're going to say a few words about qualitative response models, and then specifically the concept of a latent variable model. And then in the second set of slides dealing with the refresher, I'll go over the specification and estimation of the classic Probit and Tobit. So qualitative response models are models where the dependent variable is not continuous. The treatment so far has dealt with regression models where the left-hand side is a continuous dependent variable, but in many instances in practice, that is not realistic. One obvious case is where the dependent variable is categorical. Special case of which is binary dependent variables. So you observe something or you don't observe it, 1 or 0, or categories, for example, different land uses. Each land use gets a label, but that label as such, the number that you assign to the category doesn't really mean anything. So you can't just stick a 1, 2, and 3, and 4 in as a dependent variable in a standard regression. That doesn't make any sense. And then we have two other cases that deal with only partial observations. The censored case is where you only observe the dependent variable for a subset of the observations, but you have observations on the explanatory variables for everyone. For example, this happens a lot in surveys or social experiments where there is a top income category. So, for example, you have a survey response and the dependent variable on income is either the actual income and then 200K and up or 100K and up, or house prices, you would have $1 million and up, so you don't actually observe the actual price. Then a truncated set is very similar, but in that case you don't have either of them. So the terminology is a little confusing maybe, but censoring, you can think of you have all the x's, but you don't have some of the y's. Truncated, you don't have the y's and the x's for a subset of the population. For example, again, in a lot of social experiments, there's only a target population to which they apply. Or, for example, in a lot of medical research, health research, you might have very detailed data for Medicare patients, but not for those who are not enrolled in Medicare. Or you might have them for people who do fee for service Medicare, but not the HMOs. So those would be truncated. And then a case that we've already seen before is where the dependent variable is a count. For example, a count of events. This is particularly relevant when the count is not very large, because when the count is large enough, then you can often approximate the count variable as by a normally distributed continuous dependent variable. So these are the kinds of cases. We'll focus particularly here on the binary outcome case. So we only have two outcomes, and they are coded as 0 and 1, although that's only for convenience, as we'll see soon. So what we're interested in is understanding the probability of observing observing an event, for example, and that is coded as 1. And specifically, since we're doing regression analysis, we're interested in the conditional probability. So what is the probability that something happens given that you have measurement on some characteristics of that event or of the person participating in that event? For example, you're interested in people's choices of public transit versus a car. So you do a survey and you ask people, do you take the bus or do you take your car? And so taking the bus would be a 1, taking the car would be the 0, and then you have income, education, type of job, distance to work, etc. on the right-hand side. So we're really formally interested in the P sub I, the probability that Y sub I equals 1, given observations on explanatory variables X sub I. And we're modeling that as a general function of covariates and parameters. So in general, capital F of a vector of observables X sub I with associated parameters beta. And F is a general function, but to make this work, we really make F a cumulative probability. So it's a cumulative probability function in general. And then we're interested, again, in a regression context, in the conditional expectation. What is yi on average? So the cumulative probability makes sure that F is always constrained between 0 and 1. And so you can't have any negative probabilities or probabilities larger than 1. And because of the way a cumulative probability works, the probability that the conditional probability that you observe a y sub I equal 1, so the event happens given the characteristics, given the x sub I, is our function again, the function of xi and beta, and then the complement, the probability that nothing happens given the characteristics, is 1 minus f. And so that ensures that this function f has the right values. And so then we're going to be interested in picking a particular function f. But what we're interested in, as I said, mentioned in a regression context, is the conditional expectation of y sub I given xi. And as it turns out, because of some simple math, that conditional expectation is also f of xi beta. So the conditional expectation is the function. And the math is simple. When the event is not observed, y sub I is 0, so that zeroes out the complement, and that's why you set it up this way. So the probability that y sub I is 1 is f. Probability that y sub I is 0 is the complement, 1 minus f. On average, the average value of y sub I is this f function. Now, keep in mind that f is a cumulative probability, so the average of y sub I will not be 0 or 1, but it will be a fraction. It's interpreted as the probability of, on average, of observing an event, y sub I equal 1. And then, as you probably know, the common specification for this function f is either the logit, which we will not be spending any attention to. The logit function is the ratio of the exponential xi beta over 1 plus the exponential xi beta. The reason why we won't spend any time on it is because everything here is, we're interested in spatial dependence, and dependence requires a multivariate distribution, and the normal distribution, as I mentioned several times already, is particularly attractive because its marginals and its conditionals and its joint, they're all the same family. They're all normal distributions. That's not the case for the logit. So it's very difficult to think of a multivariate logit with spatial dependence in it. It just doesn't exist. There's other ways one thinks of spatial effects in logit models. However, the Probit model is the one where we specify the function f as the cumulative distribution evaluated of the standard normal distribution evaluated as xi beta. So is in the usual notation, that's the integral up to xi beta of the density function. So in our notation, we have phi as a cumulative Gaussian or normal distribution, and then slightly larger phi, which I've colored orange in the slides to keep them separate, as the density. In contrast to linear regression, in Probit regression, which is a form of nonlinear regression, the marginal effects are not the coefficient. So in a linear regression, if you want to find out what is the effect of changing one of the explanatory variables on your predicted value, the change of x on the change in y, that's just a coefficient. But because the Probit model is nonlinear, the or any qualitative dependent variable model in that, for that matter, is nonlinear. So the effect of a change in the explanatory variables on the outcome is no longer a constant. And so that's, if you come from a linear regression world, at first that may seem a little disconcerting, but it just means that you have to evaluate this marginal effect for different values of your explanatory variables. And particularly what you might be interested in is if explanatory variables are indicator variables. So you implement a policy, that's a 1, you don't have the policy, that's a 0. Then you can evaluate this function, and you can evaluate the partial derivative of the function for the value 0 and for the value 1, and get an idea of what is the effect of a change. So the marginal effect changes with x of I, which changes with the variable, the value of the explanatory variable, in contrast to the linear regression. And so it's a different value for each value of the explanatory variable. In practice, one often resorts to an easy kind of a cop-out solution by using the average value of x to assess the marginal effect, but that is not always, I mean, it's always correct in the sense that it is for the average value of x, but it may not give a proper perspective on how sensitive your dependent variable is to changes in different ranges of the x variable. So then, after this general introduction, we focus on a latent variable model, which is really the approach we're going to take to bring regression into these kinds of models. And conceptually, a latent variable is an unobserved variable. So it's really a concept, is something we come up with mathematically, but it's not something you can observe. And we will use the notation y star for our latent variable. And so this is something like a propensity to consume. So the propensity to buy a house, you don't actually know what that propensity is, but you know in economics it would have to do with your utility function and things like that. You only observe whether a person buys a house or not. Same with a crime, propensity to commit a crime. There would be some psychological or sociological theoretical framework that explains why crimes would happen, but you don't actually see this. It's a concept. You only see the action or not action. So you only observe presence or absence. The example in the slide, propensity to take a bus or not to take the bus is really what we're modeling, but we don't observe it. We only observe whether somebody takes the bus or not. And so with this latent variable, we construct what is called an index function model, which is a model for the unobserved latent variable. And the easiest case is the linear case, where it writes just like a standard linear regression, y star is a function of xi beta, and then an error term. And the error term will determine how we actually model this. And we get from the unobserved latent variable to the observable binary 0-1 variable through a threshold condition. So conceptually, we say there's this y star that we don't really observe, but we can think of. If that y star is large enough, crosses some imaginary threshold, then we see the event. If it doesn't cross the threshold, we see nothing. We have a 0. So then formally, we can spell out this threshold condition arbitrarily at 0, and we'll see in a little bit why that is okay. So we set if the latent variable is positive, we equate that with observing a 1, and when the latent variable is not positive, negative of 0, we don't observe anything. And then we see that by definition, the probability of observing an event, the conditional probability given some explanatory variables, is the same as the probability of having a positive latent variable. But keep in mind, this latent variable is not observed. So we still need to figure out a way to connect this latent variable to observables so that we can have a condition in observables that we can connect this to, because so far this is purely conceptual. So we come up just as before with our an index function and a given probability function. So since this is all about probability of the latent variable being positive, we express that. If we take our function to be linear, then it is the probability that x sub I beta plus the error term is larger than 0. And this is where it becomes interesting, because x sub I beta is a constant that has no probability assigned to it. So everything having to do with this condition hangs on the probability distribution for the error term, just like in a linear regression. So the probability that we observe something, so the probability that y equals 1, is the same as the probability of the latent variable being positive, which is the same as the probability of x sub I beta plus ui, the error term, being positive, or after moving things around, is the same as u sub I being larger than negative xi beta. Now, that is a little awkward as such. As it turns out, for a symmetric random variable, and you can just draw a graph and look at the tails, and then you'll see that in fact this holds very easily, the probability that a random variable is larger than the negative of a constant is the same as the probability that it is smaller than a positive of the constant. And this then puts us in a more familiar framework, because the probability that a random variable is less than a constant is simply its cumulative probability. So we're back in business. We use this result to express the probability that we observe something, which is the probability that the latent variable crosses the threshold, is positive, is related to the randomness of the error term as the probability of the error term being less than xi beta, which turns out to be the cumulative the probability of xi beta. So if we have a cumulative distribution function, we plug in the value of xi beta and we get the probability out of there. Now, as I mentioned, why do we take 0? Because we have a scale issue. For example, we can multiply everything by C, and it's still the same condition. So that creates an identification problem, which is addressed in most of these types of models, and specifically in the Probit model, by arbitrarily setting the variance of the error term to 1. So for a Probit model, then, that will result in us using a standard normal distribution. Standard because the variance is set to 1. So next we'll turn to the classic Probit and Tobit specifications.